Okay, let's talk now a bit more about linear classification. Remember that the goal in classification is to take an input vector x and to assign it to one of k possible classes. Okay. The simplest case is when you have only two classes. We are talking about a binary classification problem. In the most common scenario, the classes are taken to be disjoint, so that each input is assigned to one and only one class. So take as an example classification of digits. If we are going to classify digits, each of the inputs could belong only to one of the classes. Like if we take a number, it could be even whether a 1 or a 2, but it could not be a 1 and also a 2. So they are classes that are disjoint. They can belong only to one class. So this is the most common scenario, although you can find problems in which the inputs could belong to two or more classes, but this is not common. Now, the input space is divided into regions, decision regions, and the boundaries between these regions are called decision boundaries or decision surfaces. Datasets whose classes can be separated exactly by a linear decision surface are called linearly separable. Like, for example, consider this problem. This is a binary problem in which we have two clouds of points, and in this specific case they can be perfectly separable using a line. This is a case of linearly separable problem, and of course this is let's say an easy problem. Usually you have these clouds that are overlapped, and this is a bit more complicated. Okay, for classification problems, however, we wish to predict discrete classes labels, or more generally, posterior probabilities. So in the general case, we try to focus on probabilities. What is the probability that some point belongs to some class? To achieve this, we consider a generalization of this model in which we transform the linear function, like for example a polynomial, and we transform that function using another function, which in this case is a nonlinear function, that here we are calling this function f. And this function, especially in the neural networks field, it is known as activation function. This f function, in our logistic regression problem, we used the sigmoid function. So this f would be, for example, our sigmoid function, and this expression here inside, where w is the vector of parameters, x is the input vector, and w0 is the bias, would be our polynomial. An input vector x then is assigned to a class C1 if the evaluation of that input vector equals 0 or is larger than 0, and to class C2 otherwise. So let me go back to the plot of the points. This y of x in that example would be simply this blue line. So what we are saying is, if you take a point, and that point, for example this one, is in the upper side of this line, then we will say that this is in this case of class 1. And even if it is lying in the line, exactly over the line, we will consider it to be a class 1. If it is below the line, we will consider it to be a class 0 in this example. So it is important to remember that any point that is exactly lying in the line, in this case, the evaluation of y, of this function, y, will equal 0, because that point satisfies the equation of this line. And that happens in the same way if instead of talking about a line, we are talking about a plane or a hyperplane. So let's continue here. So we talk at this point about discriminant function. A discriminant function takes an input vector x and assigns this input vector to one of the k classes in our problem. In this case, we're going to denote that class by ck, class k. The simplest representation of a linear discriminant function is obtained by taking a linear function of the input vector, as we have seen before. So this is a linear discriminant function given some input vector where w are the parameters and w0 is the bias. We evaluate this expression and we will get a number. According to that number, we will classify our point. Now, notice that the corresponding decision boundary, as I said before, is defined by this relationship, y of x equals 0. So every point in that decision boundary will evaluate the equation of the decision boundary to be 0. And also another thing that you should be able to notice is that this decision boundary, for example, consider a line, will be in a t-1 dimensional space when you are working with d-dimensional input vectors. Let me explain this again with the previous plot. Here we have our points that are in a two-dimensional space. Okay, each point is defined by two variables, x1 and x2. Okay, the coordinates of these points in this 2D plane. And our decision boundary is this line. This line, to specify a point in this line, you just need a number. Okay, if you consider this line as an object, to specify a position in that line, you just need a number over this line. So our input vectors are in two-dimensional space, x1 and x2, but our decision boundary is in only one dimension. So it's in one less dimension than the input vector. Imagine, for example, that these points were not in a 2D space, but in a 3D. So suppose that we have here dimension x3. So our space will be like a cube. Then this decision boundary would be a plane, not a line. So again, our points in that example would be in an input space of dimension 3, and our decision boundary will be a 2D geometrical object. In that case, would be a plane. And this is the same if you increase the number of dimensions. So your decision boundary will be always in one dimension less than your input vectors. Okay, so we have said that every point that is lying exactly in our decision boundary, the evaluation of that point in the equation of that decision boundary is 0. Consider two of these points. We are going to call them xa and xb, and these are lying in the decision boundary or decision surface. Since they are in the decision surface, y of xa and y of xb will be 0. We will show in the next slide that the dot product of the vector of parameters w and the subtraction of these 2 points is 0. And what does that mean? It means that this vector, the vector of parameters, is perpendicular to the vector resulting from this subtraction. Because if two vectors, when you compute the dot product of those vectors, you obtain a 0, that means that those vectors are perpendicular. And in this specific case, when we say xa minus xb, we are considering a vector that is lying exactly on the decision surface. And I'm going to show this in the next slide, but at this point it is important to see that this product equals to 0, and that means that w, the vector of parameters, is perpendicular to the decision boundary. Okay, so this is what we are saying here. The vector w is orthogonal to every vector lying within the decision surface. So this is important because then we know that the vector w determines the orientation of the decision surface. In this case, we can obtain the orientation of the decision surface, and we can also obtain, we will see that later, the distance of this decision surface from the origin. Okay, so let me try to explain why we say that this is true. So consider these 2 points, xa and xb. The evaluation of these points in the model is 0. Then if that is true, we can simply evaluate those points, and in our model, evaluating them would be simply just to write explicitly the multiplication by the parameter vector plus the bias in both cases. Then from this we can simply move w0 to the other side, and we disappear w0, and then from this we can move this this product here to the left. We have this expression, and then from here we can simply factorize the w vector, and we get to the expression that we wanted to show that it is true. And remember that this xa minus xb is or represent any vector that is lying exactly over our decision surface. Just to remember that the subtraction of vectors, suppose that these two vectors xa and xb are like this, then this vector in black can be written as the vector xa minus the vector xb. Okay, and of course, since these two vectors are exactly over the decision boundary, when we compute this subtraction of vectors, we are generating another vector that is exactly over the decision boundary. Okay, so if x is a point on the decision surface, we know that the evaluation is 0, and we can see that the normal distance from the origin to the decision surface can be given by this expression. So what are we doing here? First, we're simply taking the definition of the linear function, which is w times x plus w0 equals 0, and then we're moving the bias to the other side. Once the bias is in the other side, we simply divide both sides of the equation by the norm of w, so the magnitude of the vector of parameters, and we obtain this expression. And what is this expression? If you compute w over the magnitude of w, what you are generating is a vector which size is 1. The magnitude of this resulting vector will be 1, and it is pointing in the direction of w. So we are creating a unitary vector by dividing w over the norm of w. And when you multiply that unitary vector by x, what you're doing is projecting this vector onto the direction of w. So you are projecting this vector onto the direction of w. And then what you are doing is computing the distance from the origin to the point x. I will show this in the next slides. At this point, it is important to see that this is true, simply by moving w0 to the other side of the equation and dividing both sides by the same number, which in this case is the norm of w, the magnitude of this vector. We therefore see that the bias parameter is an important one, and it determines the location of the decision surface. So let's see this. Let's review how we can compute the projection of vectors. So consider these two vectors, A and B, and they are in an angle phi, phi, and we want to compute. We want to project this vector A over vector B, and we want to see what is the length of this projection. So this will be small a. So first, remember that the cosine of phi will be defined as a over the size of this side of the triangle, which will be the magnitude of this vector a. And we write it like this. Then from this expression, we solve for a, and we see that a equals the product of the magnitude of vector a times the cosine of phi. Also, we know that the definition of the dot product of two vectors a and b is written as the norm, the magnitude of a times the magnitude of b times the cosine of the angle between them. And from here we can get that the cosine of phi equals the dot product of the vectors divided by the product of their corresponding respective magnitudes. And then we can replace cosine of phi in this equation 1, and we get this result. We see that a, this segment of line here, equals vector a times this expression here, and when we multiply it, we can divide the magnitude of a by itself, so it becomes 1, and in the end we have this expression. And here we can see that we have a, vector a, which is this vector here, and we are multiplying that vector by vector b over the magnitude of b, which is a unitary vector pointing in the direction of b, which is exactly what we got here. Okay, here we have some vector x that is multiplied by a unitary vector in direction w. And we can see all these concepts that we have been analyzing in this picture. For example, first we have the decision boundary. In this case, it's a straight line. All the points that are lying on this line will evaluate to 0, and all the points that are in the upper side of this line will evaluate to a positive number, so they will be larger than 0, and this will be called the region 1. All the points that are below this straight line will be negative. The evaluation will be less than 0. Okay, and here we have drawn the vector W, which is perpendicular to the decision boundary, as we saw before. And in the previous slide, we saw that the distance between the origin and the decision boundary can be computed as the negative of the bias over the magnitude of W.